Brianna Knight. I'm currently a rising sophomore at UNC with a major in pre-nursing, so I get to apply this year. It's super exciting. I'm currently a member of the co-ed honors fraternity Phi Sigma Pi. I'm also a member of UNC Moonlight Dance Crew, and I also am a part of Healthy Heals Ambassador, which is a peer education group. The main reason I would like to mentor, specifically in general chemistry, would be I want to provide the help that I was given when I took those courses at UNC, because I know chemistry as a subject for many people is very intimidating to approach, and I know it was for me, but with the help of my peer educators, I was able to bridge that gap, and that's something that I want to be able to do with other people as well. Okay, so today we're going to be talking about a titration between phosphoric acid and sodium hydroxide. So it says that 50 milliliters of 0.5 molar phosphoric acid is required to neutralize 20 milliliters of sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? So first things first, we have to write out our equation and balance it. So we already have it written out for sake of time. And we immediately notice that our sodiums are in balance. And so we're going to go ahead, just to compare them, our reactants and our products, we're going to write out our elements that we have on each side. And based on the formula, we know we have 5 oxygen, 4 hydrogen, 1 phosphorus, and 1 sodium. And on the product side, we have 5 oxygen, 2 hydrogen, 1 phosphorus, and 3 sodium. So immediately we notice that our hydrogen and our sodium are out of balance. So the easiest thing to do first would be to balance our sodium by simply putting a 3 in the coefficient in front of our sodium hydroxide, which then balances our sodium, but then it messes up our oxygen-hydrogen concentration, or not concentration. On the reactant side, giving us 7 oxygen and 6 hydrogen. So next thing we have to do is balance our hydrogen and oxygen by adding a coefficient in front of our water. And since we have 2 hydrogen, the easiest thing to do is put a 3 in the coefficient in front of our water as well, which then balances our equation. So now that we know the proper stoichiometric ratio between phosphoric acid and sodium hydroxide, we can now start talking about molarity, which is equal to the moles of solute over liter of solution. So based on this, we can solve for the moles of our given reactants by multiplying our molarity with our liters. So now that we know our liters and the molarity of our phosphoric acid, we can solve for the moles of that first. But first, we have to convert our volume from milliliters to liters, and we can easily do that by dividing by 1,000, because we know 1,000 milliliters is equal to 1 liter, which then gives us a volume of 0.050 liters, 3 sig figs. All right, now that we know this value, based on our equation, we know if we multiply it by our molarity, which is 0.500 molar, we can get our number of moles of phosphoric acid, which is 0.025 moles. Alright, so now that we know that, we can plug this in to another train track method to compare with our sodium hydroxide for the stoichiometric ratio. So now that we know we have 0.025 moles of phosphoric acid, we know, based on the balance equation we did before, that 1 mole of phosphoric acid is equal to 3 moles of sodium hydroxide. So by multiplying this out and doing some simple math, we know that we now have 0.075 moles of NaOH in our solution. So now we can use this along with our molarity equation from before and the volume that's listed in our problem, which is 20 milliliters, to solve for the moles. And just as before, and I'm just going to do this under the moles to make things a little simpler, we're going to convert our 20 milliliters to liters, which gives us 0.020 liters. And then solving that out, we get that our molarity is going to be 3.75 molar for our sodium hydroxide solution.